In this video, I'm going to talk about another equation. I'm looking for real numbers x so that they are representable in this format. That basically means for some real number a, I can write x equal to root of a squared plus a plus 1 minus root of a squared minus a plus 1. So just an example here, x equal to 0. Let me just write it as 0 is equal to root of 0 to the power 2 plus 0 plus 1 minus root of 0 to the power 2 minus 0 plus 1. And also root of 3 minus 1 is equal to root of 1 plus 1 plus 1 plus 1 minus 1 minus 1 plus 1. So these two values here, 0 and root 3 minus 1, are representable in this form. And now the question is asking us to find all these real numbers. So for example, can I write 2 equal to root of a squared plus a plus 1 minus root of a squared minus a plus 1? Is it possible? Is this equation solvable? Do we have an a such that it would satisfy this equation? And I'm going to explain the answer to this question next. So let me actually simplify. Let me just introduce a notation that will simplify the whole argument. Let me write f of a equal to root of a squared plus a plus 1 minus root of a squared minus a plus 1. Okay, and this is a, and I'm looking basically what I'm looking for, and the question is just restating the problem's statement. Find all x such that for some a in R real numbers, this is basically real numbers, such that for we have that x is equal to f of a, right? And so, okay, first observation. Observation number 1. Observation number 1 is that f of minus a is equal to minus f of a. And moreover, and also let me actually say observation 2 here. Observation 2, I have f of a is positive for a positive, right? The first observation is sort of clear. Why? And the reason for it that f of minus a is root of a squared minus a plus 1 minus root of a squared plus a plus 1. And this is basically minus f of a. So I'm swapping the order of these two terms here by just writing using minus a instead of a. And the second argument why that's the case, why that's true, I need to show that root of a squared plus a plus 1 is larger than root of plus 1 for a, a non-negative. And notice that the both hand sides, so here, so both hand side, the inside is square root is a non-negative number, obviously, right? So this inequality holds if and only if we have a squared plus a plus 1 larger than a squared minus a plus 1. And this is true if and only if 2a is non-negative, which is true because a is non-negative, right? And notice that the reason that I mentioned here we have non-negativity under the square root is just something to note, because otherwise we would be working with complex numbers and none of these would make any sense, right? Okay, so we have these two observations, and from these two observations, I'm going to conclude that if x is f of a, if and only if minus x is f of minus a, f of minus a, right? And so I can just focus on positive numbers. Basically means I'm going to reduce the problem. It's like question A is find all non-negative x such that x is equal to f of a for some a non-negative. Notice that here I showed that f of a is non-negative for a non-negative, but this is a vice versa a statement, right? Because basically here I could write f of a non-negative if and only if a is non-negative. And the reason why that's the case is because of this simple equation we have here. And so we can also say that f of a is non-negative if and only if a is non-negative. Okay, so now I'm reduced to non-negative values for a. And notice that f of 0 is 0, right? All right. Okay. Here we have like the first few observation. And next, I'm going to discuss some fact from calculus, which is basically the core part of this equation, and that would be the intermediate value theorem. Intermediate value theorem is as follows. If f is a continuous function defined on some interval, let's say a and b, then all the values inside f of a and f of b is attainable by f. That means there exists some x between a and b such that f of x is equal to s. And that's really what this image is also showing. We have f of a, we have f of b, and we have some value s between f of a and f of b. And here you see there exists at least one x such that f of x is equal to s. Okay, and now consider three observations. One of them is observation number 1, f of 0 is 0. Observation number 2 is that f of a is always less than 1. And observation number 3 is that the limit of f of a a goes to infinity is equal to 1. And the first one is clear, right? And I'm going to show both of these. But assuming that these three holds, then what would be the answer to the question in view of the intermediate value theorem that we discuss here? Assuming that these three observation holds here, what would be the answer to the question that we have? And so the answer is assuming assuming observation 1, 2, 3 holds, then for all x between 0 and 1, 0 included, 1 not included, excluded, there exists, this is a notation for existence, there exists a non-negative such that x is equal to f of a. And this was just for the non-negative a part, right? And moreover, for all x strictly between -1 and 1, there exists a real number such that x is f of a. Okay, so now I'm left with showing observation 2 and 3. Let me rewrite observation 2 here. I want to show that root of a squared plus a plus 1 minus root of a squared minus a plus 1 is less than 1. This is for all a non-negative, right? Because otherwise a would be, the left-hand side would be negative, and there's no point in actually showing this. It would hold trivially. And so this holds if and only if root of a squared plus a plus 1 is less than root of a squared minus a plus 1 plus 1. And this holds if and only if raise the two sides to the power of 2. I have a squared plus a plus 1 is less than a squared minus a plus 1 plus 1 plus 2 times a squared minus a plus 1. Just simplify, get rid of a squared here, here, and 1, 1. Let me actually do this. This would go with this. This would go with this. And I would have, I'm left with what here? I'm left with 2a plus 1 is less than 2a squared minus a plus 1. And in order to show this, this is if and only if a plus, oh, there is a mistake here. There's a mistake here. And this should be minus 1. And this should be minus 1. And this minus 1 as well. Less than root of a squared plus a plus 1. Now I want to show this equation, this inequality, this bond here. So there are two cases. One of them is, I have another typo here, minus 1. Okay, so there are two cases. If a is less than 1 over 2, then the left-hand side is negative and the right-hand side is positive. There's nothing to show. So we can just assume that a is larger or equal to 1 over 2. But probably we don't need to work with cases. We are going to just use absolute values inside, right? So let me write the right hand side here as root of a squared minus a plus 1 is equal to root of a 1 plus 3 divided by 4, right? And this is going to be larger than the absolute value. Or I can write one more step here just to make it easier to follow. A minus 1 over 2 to the power 2. You see I got rid of this term 1 plus 3 over 4, which is a positive term. And I definitely get something smaller. And this is equal to the absolute value of a minus 1 over 2. And this is obviously larger than or equal to a minus 1 over 2. And so that's it. That's we showed that this and this is the left hand side. Sounds good. Okay, we proved observation 2. And now we are left with observation 3. Let me write what exactly we want to show. A goes to plus infinity, root of a squared minus 1 plus a squared plus a plus 1 minus the other term. I want to show that this is equal to 1. Before trying to actually show this, just to get an idea why this should be true, like a pseudo formal argument, not formal, not formal argument here. We have root of a squared plus a plus 1 is a, right? And also so okay, now if a is large, I can basically get off this term because this is going to be a huge term and this is going to be a very small one. The same for here. This is going to be huge and this is small. Here by large, I mean like I'm talking about something like a being like 1 0 0 0 0 0 0 0, right? In that case, this term here, the first term is huge and the second term is very negligible. So basically I can get rid of this. And so I can sort of say that here we have a plus 1 over 2, the same for here. And now if you make the deduction, if you do the subtraction, you get like a plus half minus a minus half, and you get 1. So sort of in the limit, this function is behaving as constant 1. And so now you should have a better feeling of why this should be true. But as I said, this is a not formal argument. This is not rigorous. If you want to make a rigorous argument, you have to go a different way. So here, limit of, let me just rewrite the expression that we had. And this is equal to a 2a divided by notice that here I multiplied the numerator and denominator by this factor. And now this is equal to limit of a goes to plus infinity, 2 divided by root of 1 plus 1 over a plus 1 over a squared, plus another term here, root of 1. Oops, I had a typo here again. This should be minus, and here I have 1. Okay, and if goes to infinity, this is constant, this is 2, and this part goes to 0, this part goes to 0, 0, 0. So I would get limit of a goes to plus infinity, 2 divided by 2, which is equal to 1. So the third observation is also proved. And all of this put together would actually give us a proof of what we showed here, that the answer to the question is basically any real values between -1 and 1, strictly between -1 and 1, is representable in form of f of a for some real numbers, real number a. All right, feel free to ask me any question. I would do my best to respond as soon as possible.